Hello, everyone. Welcome to pre-lecture 26. We're going to be talking about cell potentials, electrochemical cell potentials, and the Nernst equation in this pre-lecture. So what we've covered so far, at least part of what we've covered in electrochemistry, has been talking about voltaic cells, which are also called galvanic cells, and how they generate electrochemical potential. And so a reminder that we have a redox reaction take place separated by an external circuit that can perform work, as well as a salt bridge that helps balance our charge as the redox reaction occurs. And so we end up with a cathode where we have a reduction reaction happening. So silver would be our cathode in this example, where we have silver that is dissolved being reduced to silver metal through a reduction reaction, and then our oxidation reaction, our solid copper is turning into copper 2+, so going from a solid to being dissolved as it is oxidized, right? So within each electrochemical cell, you can measure the electrochemical cell by, or the potential of the cell rather, I should say, by taking the potential of the cathode half reaction and subtracting the potential, so uppercase E, of the anodic reaction. And typically, we put this all on a scale against the standard hydrogen electrode. So if you see uppercase SHE, that is used to set the scale for our electrochemical potential at 0 volts. And so what the standard hydrogen electrode looks like, so you have H2 gas and you have a 1 molar solution of acid and a platinum electrode. And essentially we have just defined that as being our 0 volts. And we'll maybe talk a little bit more as to why that is in class. So by connecting our standard hydrogen electrode or any electrode to another half reaction, we can determine a standard reduction potential. And so as electrons flow, we could hook up a voltometer, something to measure our potential. This is what we'll be doing in lab this week, partially at least, and we would measure a potential of 0.337 volts. And so all of these values are tabulated in the back of our textbook in table 17.1 or appendix L in your textbook. Any half reaction, so all of these are written as reduction half reactions, I should say. So every reaction you'll see here is written as a reduction reaction where we have electrons on our reactant side. And from there, we measure a reduction potential. So anytime you see this E naught, that is called a reduction potential, and that is the potential of that half reaction under standard conditions. And so the more positive it is, the more oxidizing something is, and the more negative it is, all the way down to lithium, the more reducing that thing then becomes, okay? And so species with more positive reduction potentials are things that are easily reduced, whereas species that are more negative are more easily oxidized. And so hopefully you can keep that straight. I know it's a lot of positives and negatives, but something good to keep in mind: if it has a very positive reduction potential, it is easily reduced. Very negative reduction potential means very easily oxidized. Okay, and so based on what you know with our cathode and anode, say we have an electrochemical cell made out of silver and barium, and we wanted to know which is going to be oxidized and which is going to be reduced. And so if you look, I've put little boxes here around silver and barium. So figure out which would be reduced and oxidized. So if you want to pause the video, take a moment to think about that. I'm going to go on though. So we would look at our reduction potential for silver first and see that that is more positive. And so it will be reduced, and then barium will be oxidized. And so Ag plus will be reduced, barium will be oxidized. What that means, if we want to calculate our overall cell potential, is E cell is equal to our cathode minus our anode. A reminder that reduction takes place at the cathode, oxidation takes place at the anode. And so our cell potential would be 0.7996 minus negative 2.912. And that gives us an overall cell potential of 3.7116 volts. Okay. For spontaneous cells, which is most of what we'll be dealing with, again, those could also be called galvanic or voltaic cells, the E cell potential will always be positive. Okay. Something to consider here that is maybe non-intuitive, but you do not need to multiply any sort of reduction potential value, so the actual numerical value there, even if your reaction is multiplied to make coefficients balance. So if we were balancing, for example, that electrochemical reaction, we would need to multiply our silver reaction by 2 so that we transferred 2 electrons instead of just 1. Even though we would multiply the chemical species by 2, we would not multiply the reduction potential, okay? All right, so to try and kind of put a nice bow on everything, our reduction potentials can actually be related to our Gibbs free energy and equilibrium values because they are all measurements of spontaneous processes. And so we have these 2 equations here where we can relate the potential of our cell to our equilibrium constant K by relating it with R and T, which are, of course, our ideal gas constant, temperature in Kelvin. N is then the number of electrons transferred in the electrochemical cell, and F is something new to us called Faraday's constant, and that is 96,485 coulombs per mole of electron. And so pretty much any electrochemical equation is going to have Faraday's constant in it. It's kind of like the ideal gas constant, but for electrochemistry. So that is what F is. We also have an equation that relates our cell potential to our Gibbs free energy. Okay, and so what we can do is actually construct this super cool triangle here where we can relate our equilibrium constant with our delta G value. We can also relate our equilibrium constant with our cell potential, relate cell potential with Gibbs free energy. And all of these are then, of course, equal to each other. And so for any sort of spontaneous reaction, all of the following will be true, that K will be greater than 1, delta G will be negative, and our cell potential will be positive. Okay, the opposite then, of course, is true. For non-spontaneous reactions, K will be less than 1, delta G will be positive, and E cell will be negative. Okay. So that's all we're going to be talking about in the pre-lecture today. If you have any questions, of course, feel free to let me know. Otherwise, take care, and I will see you in class.